Okay, let's touch on the weathering of marine sediments and the ocean crust, and of course reverse weathering. We are revisiting some of these terminologies because we are looking at fluxes and balance of global carbon cycle. Before we had looked at it in terms of processes and other points that we made before about how carbon cycle has evolved. And here extended, this table is looking at expected changes in pH, alkalinity, and dissolved inorganic carbon in anoxic pore fluid resulting from methanogenesis. Anoxic usually means there are species which can degrade hydrocarbons that's available and convert it into DIC via methanogenesis. Carbonate precipitation and marine silicate weathering is all included here, just to get a sense that marine sediment weathering and crustal weathering are an important part of the overall atmosphere-ocean CO2 balance. So methanogenesis we talked about before, obviously will decrease the pH. It will not affect alkalinity, and dissolved inorganic carbon is increased. Carbonate precipitate methane is easily oxidized, and then as it seeps, so methanogenesis happens, let's say, by the worms living in the sediment in anoxic conditions. The methane pressure then makes it flow out into these pore holes and so on that we had talked about, and various reactions then release that methane into DIC and affect pH and so on. Carbonate precipitation, pH would be decreased. Obviously you are taking away CO2. Alkalinity would decrease because of the detailed reactions, and it will also decrease DIC. So this is kind of not as intuitive, but you have to understand that alkalinity is a balance of all the proton receptors, basicity as we called it. So you can decrease pH and decrease alkalinity in these situations when you precipitate carbonate. Okay. Marine silicate weathering will increase pH. That's obviously going to be counterintuitive as well. We are thinking on land, we are taking CO2 plus H2O and doing silicate weathering, but when we have marine silicate weathering, we are increasing pH and increasing alkalinity and increasing dissolved inorganic carbon. So when you include methanogenesis and carbonate precipitation together, pH will decrease. Now alkalinity is going to decrease. Okay, here it was no change, and carbonate precipitation was decreasing it. And DIC is decreasing. So DIC depends on relative reaction rates of methanogenesis and carbonate precipitation. So the chemistry of this gets more and more complicated. If you combine methanogenesis with marine silicate weathering, then you get pH decreasing but alkalinity increasing, which makes sense, and DIC increases. So here pH now depends on relative reaction rates of methanogenesis and marine silicate weathering. So if you combine all three, pH will decrease, alkalinity will increase, and DIC will increase. So this is what we would be interested in. pH, alkalinity, and DIC depend on relative reaction rates of methanogenesis, carbonate precipitation, and marine silicate weathering. So very hairy details which we are not going into, but marine sediment weathering is an important player in alkalinity balance, PCO2 at the sediment, or could be in shallow waters or deep waters, but we are looking at geologic time scales, which means the atmospheric oceanic PCO2 are eventually going to be affected as well. So long-term regulation of carbon cycle and CO2 are going to depend on marine silicate weathering as well through methanogenesis, carbonate precipitation, and marine silicate weathering. Looking at continental crustal controls on carbon cycle, this is called the slow carbon cycle. So here all carbon fluxes represent minima and maxima from 230 million years ago to present day. From this paper, we are just using this as an example. So we are looking at a schematic diagram showing oceanic crustal carbon cycle. Values indicate maximum and minimum carbon fluxes for the oceanic crustal carbon reservoirs since 230 million years ago. Downward pointing arrows indicate that the carbon is sequestered into the crust or the mantle. Upward pointing arrows indicate carbon flux into the atmosphere. The ocean crust acts as a sink or source of atmospheric carbon depending on its changing capacity to hold CO2 through time, subject to fluctuations in the age area distribution of ocean crust, changes in bottom water temperature. The percentage of subducted carbon degassing into the atmosphere is not well known, and we show n-member fluxes based on 35 and 65% of subducted carbon escaping into the atmosphere. So just remember the broad scale processes that the ocean crust is constantly forming, spreading out, and even there are models to look at these time scales, and this is understood by looking at the reversing magnetic fields as new crust forms and spreads out. There is a switch in the magnetic poles, and that is recorded in the crust, and the crust obviously is heavier, almost 3 times heavier than the continental crust, and it subducts under the continental crust, and there is weathering happening, and of course there is degassing happening, as we already saw. So these are the numbers we are looking at: 5.3 to 9.8 million tons of carbon per year going from continental crust to the atmosphere. This is for 65, when you assume 35% degassing versus 65% degassing, obviously you get very different numbers. The mantle and lithosphere may also get some CO2 fluxes from the ocean crust. Sorry, this is the continental crust. Total carbon storage in the ocean crust is 2160 to 2650 million tons as a reservoir. So we have asthenosphere and the ocean crust interacting here. So all we have why do I keep messing this up? Oceanic crust releasing 4.5 to 14.8 million tons of carbon per year, which is obviously a large uncertainty. And the ocean crust is also pumping down into the mantle lithosphere 4.0 to 18.3 million tons carbon per year, and there is transport happening down the lithosphere of 15.1 to 58.4 million tons carbon per year. I don't know why I'm bumbling, sorry. Okay, so there is the outgas or CO2 release to the atmosphere. So we are going through all the ocean processes. Obviously things cannot go directly from the ocean crust to the atmosphere. They have to go through the ocean carbon cycle, but the estimated release into the atmosphere is from 0 to 10.9 million ton carbon per year, but there is a uptake sequestration into the ocean crust of 0 to 15.2 million tons carbon per year. Okay, there is an M missing there. So what do I want to say? Basically that the continental crust is also a big part of weathering, and we already mentioned before that estimates vary, but it's possible that majority of the weathering controls on atmospheric and oceanic PCO2 is coming from ocean crust weathering. Okay, so at least keep that in mind. Now to look at reverse weathering to finally come to the conclusion of this weathering contributions in terms of fluxes in carbon cycle. Obviously we have silica that has arrived from weathering reactions. There is aluminum compounds, and there are divalent cations like magnesium, potassium and sodium, and there is of course alkalinity, so HCO3 minus aqueous, and based on various drivers which way the reaction goes, there is always nuclei formation happening, which basically is a sink for magnesium, calcium and sodium, but it's also consuming alkalinity and releasing CO2. But this is what is called internal cycling. So this is already in the system. It's not new CO2. It's just going from alkalinity into pH. And nonetheless it's a very critical control, and some past events have been looked at in terms of the potential control. So this is the reverse weathering, right? So this is not directly the same as the weathering we talked about before in terms of H2O plus CO2 weathering silicate rocks and carbonate rocks. This is part of the nuclei precipitation process. Okay, so we call it reverse weathering because we are releasing CO2 and H2O in these reactions, and obviously that affects the carbon cycle nonetheless in terms of the residence times. For example, if CO2 is put back into the system by reverse weathering, then additional processes are needed to take it out, so you have to worry about how it affects the long-term climate regulation. So past events have been looked at to argue that geographic reorganization of biogenic silica deposition affects leads to decreased mixing of reactive silica and aluminum on seafloor, which results in a reduction in global orthogenic clay formation. So if you alter these, you are going to alter this and the sinks of these divalent cations, and that's going to affect the removal of seawater magnesium and increase the seawater magnesium to calcium ratio. And there is also increased ocean alkalinity, because if clay formation is reduced, then alkalinity is not consumed, and that's going to result in decrease in atmospheric PCO2 on some time scale after you go from the bottom sediments to the through the ocean carbon cycle into the atmosphere, and that can result in global cooling. So some past temperature events have been reinterpreted in terms of the role of reverse weathering. We already saw this before. Here we are looking at each contour representing a different alkalinity to silica consumption ratio. So that's the reaction we just looked at. The root of each curve indicates pre-industrial PCO2 here at 280 ppm. This is repeated here, sorry about that, and a reverse weathering silica flux of about 0.5 teramole per year. So that's the FRW shown here. 10 PIAL denotes the estimated minimum threshold that mitigates runaway icehouse conditions. The strength of silicate weathering feedback is set at 0.3. The point again is that atmospheric PCO2 is indeed regulated by reverse weathering reactions at the bottom of the ocean, which depends on these various factors like alkalinity to silica consumption rates and the silica weathering feedback. And the argument has been about whether, for example, when we talked about vascular plants and their evolution, whether they increased weathering rates or they just affected the silicate weathering feedbacks to produce temperature change and CO2 change. And here we are talking about reverse weathering affecting atmospheric CO2 as well. So we will come back and look at some degassing reactions, but obviously we have to go through these to understand the long-term carbon cycle and how long-term climate has been regulated because of the changes in carbon cycle. Of course, there is a feedback. When temperatures change, carbon cycle is affected, but more directly when CO2 changes, there is the greenhouse effect and temperature changes. Okay.